Welcome back to Neural Intel.
Oh.
If you are a regular listener, you know exactly how this works.
Yeah, you know the drill.
We don't do the surface level stuff here. We don't just, read the headlines about which chatbot is currently hallucinating or which stock price is up 3%.
No.
We take the stack of papers, the dense interviews, the technical documentation, the stuff that usually makes your eyes glaze over, and we really tear it apart to find the signal.
That is the mission, right? We extract the signal from the noise, and for those of you who want to see the raw data, and I mean the code snippets, the math, the architectural diagrams we might reference today, you really need to head over to neuralintel.org.
That's where the homework is.
That is where the real work happens. And of course, make sure you are subscribed on YouTube, Apple Podcasts, and Spotify. You just do not want to miss a deep dive, especially when things are moving this fast.
Well, speaking of moving fast,
Yeah.
today is, well, it's a big one. We are looking directly into the mind of Dario Amodei, the CEO of Anthropic. Now, usually when you hear from a CEO, it's a lot of corporate fluff. You know the drill, synergy, paradigm shifts, delighting the customer.
All the buzzwords.
Exactly. But Dario is different. He's a physicist by training. And so when he talks in probabilities, compute cycles, and scaling laws.
He is very much an engineer's CEO, and the picture he paints in this recent interview he did with Urkesh Patel is intense.
Intense is a good word for it.
Yeah. We are not talking about a better spell checker here. We are talking about a specific, quantified prediction that puts us potentially 2 to 3 years away from having, and this is a direct quote, a country of geniuses in a data center.
A country of geniuses. It's such a striking image. It really sounds like the setup to a sci-fi novel.
It does.
But our job today isn't to get swept up in the sci-fi vibes of that quote. Our job is to unpack the technical justification for it.
Mm-hmm.
Why does he think that's even possible? Is the exponential curve of AI progress actually holding steady, or is it about to hit a wall, like so many critics keep saying?
That really is the trillion-dollar question, isn't it? Is the curve flattening, or is it going vertical? And if it is going vertical, what happens to, well, everything? The economics, the safety, the geopolitics of the world when it does?
Because if he is right, the world in 2027 looks fundamentally different from the world today.
Fundamentally.
Exactly. So we aren't here for the hype. We're here for the mechanics. And speaking of mechanics, I think it's time to ground this conversation right out of the gate. Let's hit our first check-in.
Okay, let's do it. This is the neural signal check.
All right, lay it on us. What is the real signal here that we should be paying attention to?
The signal is that while the media is totally obsessed with the user interface, can the bot write a poem? Can it make a funny picture? Does it sound like a human?
All the front-end stuff.
Yeah, all the front-end stuff. The real story is hidden in the math of scaling. The signal is what Amodei calls the big blob of compute hypothesis. And more importantly, it's the technical realization that reinforcement learning, or RL, which, everyone thought was the separate, complex, different beast, is starting to learn mathematically identical to pre-training scaling laws.
Whoa, okay, hold on. So you're saying it's all just one big curve?
That's what the data is suggesting.
Yeah.
Exactly. It suggests that the magic isn't in some new clever architecture we haven't discovered yet. The magic is in the scale itself.
Wow.
And that has massive, massive implications for the next 24 months because it simplifies the roadmap. It means we don't need a miracle. We just need more power.
Wait, let's unpack this. Our source material is this incredibly dense interview. We've got notes here on the end of the exponential, the physics of scaling, the economics of running these massive labs, which is a whole fascinating topic on its own.
It's a crazy topic.
Yeah, and the technical implementation of constitutional AI.
And we really should start with the physics. I think that's the foundation for everything else. Because if the physics don't work, the timeline doesn't work. It doesn't matter how much money you throw at it if the laws of, thermodynamics or information theory say no.
Okay, let's do it. Segment 1, the big blob hypothesis. I have to say, I love this name. It just sounds like a monster from a 1950s horror movie.
The blob that ate the data center.
Exactly. Yeah. But Amodei actually wrote a document with this title way back in 2017, didn't he?
That's right, 2017. And you have to think about where we were in 2017. GPT-1 hadn't even really broken through yet.
It was a different world.
A completely different world. The prevailing wisdom in the AI community was that advancement required cleverness. You needed a specific trick for translation, a different trick for playing chess, a whole different architecture for vision. You had people working on robotics as a totally separate field from language.
It was a very fragmented world. You were a vision guy or a language guy or a robotics guy, and never the twain shall meet.
Precisely. And Amodei and his colleagues, they look at this landscape and they say, you're all overthinking it. His hypothesis was that all those clever tricks, all those hand-coded features, they don't matter nearly as much as we think.
So it's not about being smart, it's about being big.
In a way, yeah.
Hmm.
He argued that there are really only 7 ingredients that matter. If you get these 7 right, the blob it absorbs everything else. It absorbs the cleverness.
Okay, I have the list of the 7 ingredients here. I want to run through them because this is effectively the recipe for that country of geniuses. Ingredient number 1, raw compute.
Self-explanatory. The most obvious one. You need massive amounts of FOVS, floating point operations per second. The bigger the engine, the faster you go. Simple as that.
Number 2, quantity of data.
Also pretty straightforward. You need to feed the beast. You need tokens, trillions and trillions of them. If you run out of data, the compute just spins its wheels.
Got it. Number 3, quality and distribution of data. Now, this one seems a bit more nuanced. It's not just more, it's better and broader.
This is critical. This is so important. It can't just be a lot of data. It has to be a broad distribution of data. Amodei is this great example of GPT-1. Do you happen to know what GPT-1 was primarily trained on?
I'm guessing the internet.
Yeah.
Or maybe Wikipedia.
That's what you'd think. But no, actually, it was a data set called book corpus, which was mostly self-published books and fan fiction.
Wait, really? Fan fiction? So you're telling me the grandfather of modern AI was basically raised on Harry Potter alternate universes and vampire romances?
Essentially, yes. And because of that very narrow distribution, it was mostly literary text, dialogue, narrative. It didn't generalize well at all.
Couldn't do other things.
It couldn't do math. It couldn't code. It was only when they moved to GPT-2 and scraped the actual open internet Reddit links, Common Crawl, the messy stuff, that they got that broad distribution. That diversity is what unlocked the generalization we see today.
So fan fiction wasn't enough to build AGI. That is honestly a relief.
It's a start, maybe.
If the singularity was birthed from bad romance novels, I would be very, very worried about the alignment problem. Okay, number 4 on the list, training time.
Right. You have to let it bake. You can't rush the gradient descent. It's a physical process of optimization. It takes as long as it takes.
Number 5, objective function.
This is a big one, a really big one. The objective function, so the goal you give the model, it must be able to scale indefinitely. If your goal is just play tic-tac-toe, well, the model learns it almost instantly, and then it stops learning. It tops out.
There's nowhere else to go.
There is no more better after you solve it perfectly. But an objective like predict the next token on the entire internet or solve this complex reasoning problem, those are objectives that can scale to the moon. They are effectively infinite.
Number 6 and 7. I'm grouping these together because they sound like the boring but necessary engineering headaches. Normalization and conditioning.
This is the plumbing. It is absolutely critical, and it's all about numerical stability. When you are training a model with billions or trillions of parameters, you are doing these massive matrix multiplications, and if the numbers get too big, they explode. That's called exploding gradients.
And if they get too small?
They vanish. Vanishing gradients. You need to ensure that as you pour more and more compute into the system, it doesn't just crash or diverge into mathematical chaos. Amodei uses this great phrase, a laminar flow of compute.
Laminar flow. That's a fluid dynamics term, right? Like water flowing through a pipe really smoothly?
Exactly. In fluid dynamics, laminar flow is smooth, it's orderly. Turbulent flow is chaotic, mixing, inefficient. In AI training, you want the compute to flow smoothly through the neural network updates without mathematical turbulence or any bottlenecks.
You need smooth pipes for the numbers to flow through.
You got it. If you have those 7 things, the compute, the data quantity, the data quality, the time, the objective function, and the stability to keep it all running, the specific architecture becomes secondary. The blob just works.
And he's saying this hypothesis from 2017 still holds up today. That's like an eternity in AI years. That's like saying a theory from the 1800s holds up in quantum physics.
He says he hasn't seen much that contradicts it. And this brings us right to the RL revelation that we mentioned in the signal check. Because this is the new frontier. This is the stuff happening right now inside the labs that no one's really talking about.
Right. Because 3 years ago, we were all looking at these neat, clean loss curves for pre-training. We knew if we added more data and more compute, the model got smarter at predicting the next word. It was a straight line on a log graph.
It was predictable.
Very predictable.
But now we have reinforcement learning. We have models doing math, coding, thinking before they answer, all that chain of thought stuff. My intuition says that has to be a different process. Is that a different curve?
That is the trillion-dollar question. And Awadei's answer, which is kind of shocking, is no.
No.
No, it is not a different curve. He argues that RL is scaling exactly like pre-training. So it's log linear. You just double the compute. You get a constant reduction in error, even for reasoning.
It appears so. And he points out that other companies, DeepMind, OpenAI, they've all found this too. If you train a model on, say, math contests, the improvement in its performance is log linear with the amount of training time or the amount of samples you generate. It's the same physics.
That is fascinating. So essentially, pre-training gives you the base capability, the raw knowledge of the world, let's say.
The raw material.
And RL is just another phase of scaling that refines it towards a specific goal.
Correct. He compares it directly to the shift from GPT-1 to GPT-2. Just as GPT-1, trained on fan fiction, needed more diverse data to generalize, RL is currently moving from these very specific tasks, like solving a single math problem, to much broader generalization. We are basically seeing the big blob eat RL just like it ate language modeling before.
So the distinction we make between learning facts and learning to reason might just be an artificial one we've created. It's all just learning.
That is the big implication. It's all just compression of information. Whether that information is the capital of France is Paris, or the way to solve this integral is to apply this specific rule, the neural network seems to treat it in a very similar way. It just finds the pattern, compresses it, and predicts the outcome.
Wow. This actually leads perfectly into his mental model of where these LLMs sit compared to biological intelligence. I found this analogy incredibly helpful to visualize what's happening because, sometimes it feels like we're building an alien brain, and other times it feels like we're building a human brain.
Yes, the hierarchy of learning. He breaks it down into these three distinct layers.
Okay, so the layers are, let's see, layer 1 is evolution, layer 2 is human lifetime learning, and layer 3 is in-context learning.
Right. So let's start at the bottom with evolution. Evolution is the ultimate pre-training run. It took billions of years. It took an unfathomable amount of compute. Every single organism that ever lived and died was a data point in this experiment.
That's a great way to put it.
And what did that process produce?
It produced the hardware, the structure of our brains, our instincts.
It produced the priors. That's the key. Your brain isn't a blank slate when you're born. Evolution has pre-wired it to recognize faces, to have a propensity for language, to understand basic physics like objects fall down. A baby knows a lot more than a random number generator. A baby knows that if I hide a ball behind a blanket, the ball is probably still there.
Object permanence. But LLMs are random number generators when they start, right? They're just random noise.
Exactly. They start as random weights, just Gaussian noise. So pre-training an AI, that massive, massive run that costs $100 million or $1 billion, that's doing the work of evolution, it fills that huge gap between random noise and human at birth.
Okay, that makes perfect sense. So pre-training equals evolution. Now let's jump to the other end of the spectrum. You have in-context learning. That's what happens when I paste a document into Claude and say, summarize this. It learns the content of that document instantly.
Right. That's basically working memory. It's short-term adaptation. It's incredibly fast, but it's also ephemeral. As soon as you close that context window, it's gone. It's like you read a Post-it note and then you immediately throw it away.
But there's this huge missing link in the middle, the human lifetime learning piece.
Yes, and this is the crux of the problem right now. Humans learn permanently over the course of a lifetime. We don't reset every single time we go to sleep. We accumulate skills, we become tenured, we learn office politics, we learn our spouse's favorite color.
And LLMs right now mostly don't do this.
Not really. They have the evolution part, which is pre-training, and they have the short-term memory part, the context window, but they lack that crucial middle layer of becoming a senior engineer over 10 years.
So does Amodei think this missing link is a showstopper? Because if the model can't remember anything from yesterday, how can it run a company? How can it possibly be a genius if it has amnesia every morning?
It's a bottleneck, certainly. And this transitions us perfectly into the timeline he lays out. He doesn't think it's a showstopper for achieving massive capability. He thinks we can just brute force our way around it.
All right, let's get to the numbers then. The prediction. Because this is the part that made all the headlines, but the context we've just discussed is what really matters.
Okay, so here it is. He is 90% confident that by 2026 or 2027, we will have models capable of performing as a country of geniuses in a data center.
90% confidence. That's absurdly high. for a prediction that is effectively 2, maybe 3 years away. In the tech world, usually 2 years away means 5 years away, and 5 years away means it's never happening.
Oh, it's an incredibly strong claim. He does add a caveat, of course, about irreducible uncertainty. Things like, global wars, massive supply chain collapses, China invading Taiwan. Those things might push the probability down.
Black swans.
Exactly. But on the technical feasibility, just on the question of can we build it, he sees the path clearly. He thinks it's almost a done deal. The tracks are laid, the train is moving, and it's picking up speed.
So what does a country of geniuses actually look like in practice? Because genius is such a loaded word. Are we talking about passing the bar exam? Because they can already do that pretty well. Are we talking about scoring 1 in 60 on an IQ test?
This is a great question, and it's time for another neural signal check.
Let's do it.
We need to define this technical capability level properly. It is not just about passing some static multiple choice test. Amodei makes a really important distinction between verified tasks and unverified tasks.
Verified tasks. Those are things like coding, right?
Yeah.
Where you can run the code and it either works or it doesn't. The compiler is the judge and jury.
Correct. It's a closed loop. The environment gives you unambiguous feedback. And for those verified tasks, Amodei thinks we are basically there, or we will be in the next 12 to 18 months. The model generates a solution, the environment verifies it, done.
But the country of geniuses benchmark requires success in the unverified tasks.
The messy stuff.
The messy stuff.
Right.
Like writing a novel, or planning a mission to Mars, or inventing a new drug. Things where you can't just run a unit test to see if it's correct. Things that require judgment and taste.
Exactly. And the specific test case he uses, which I love, is the video editor test.
I thought this example was so perfect because it's so relatable. He says, imagine a video editor working on this very interview that we're recording right now.
Right.
They aren't just cutting clips based on a script. They're making hundreds of tiny judgment calls constantly. Oh, Dario scratched his head there. That looks awkward. Let's cut it. Or this point is really interesting. Let's zoom in a little bit.
It requires taste, that's the word. It requires understanding the host's preferences, the audience's likely reaction, the pacing, the overall narrative flow. A great video editor knows what you want before you even ask for it.
And this brings us right back to that missing link of lifetime learning. If the model resets every session, how does it learn my specific taste over 6 months? How does it become my tenured video editor? If I have to explain my style guide from scratch every single morning, it's not a genius, it's an intern. And a pretty annoying one at that.
Exactly. So Amodei proposes 2 technical solutions to this bottleneck. The first one is pretty brute force. Context extension.
Just make the window bigger.
Much, much bigger. Millions of tokens. You just shove the entire history of your relationship, every edit you've ever approved, every Slack message, every style guide, into the prompt every single time.
So it's not learning, it's just reading really fast.
Precisely.
Right.
And he argues this is an engineering problem, not a fundamental research problem. It's about something called KV cache storage.
KV cache, key value cache. We hear this term a lot in optimization papers. Can you explain that for the non-engineers in the audience? What is that?
Sure. So when an LLM processes text, for every token, it calculates these intermediate mathematical representations, keys, and values. And it stores them so it doesn't have to recompute them every time it generates the next word. It's like keeping all your notes open on the desk while you write an essay.
So it's a memory-saving trick.
It is, but that storage itself takes up a massive amount of very expensive GPU memory. So making the context window huge, millions and millions of words, means that cache becomes absolutely enormous. It's a plumbing problem. How do you juggle that massive amount of memory efficiently across thousands of GPUs?
But plumbing is solvable. It might be expensive, but it's solvable.
Yes. It's solvable with enough engineering effort and money. The second solution he proposes is continual learning, actually updating the model's weights on the fly based on new interactions.
The holy grail, true learning.
Right. Amodei thinks this might actually be solved in 1 to 2 years. But, and here's where it gets really interesting, he also thinks it might not even be necessary to get to that genius level.
Really, you don't need real learning.
He suggests that a massive context window might be good enough to simulate lifetime learning. If you can fit 1 million words in the context, that's days or weeks of human reading time available instantly. That might be enough for the model to grok the job without permanently changing its underlying brain.
So the country of geniuses might just be a country of amnesiac geniuses with a perfect photographic short-term memory.
That is a very, very accurate way to put it. They wake up every morning with a totally blank mind, but they can read your entire corporate history in 10 seconds flat and then act as if they've been a loyal employee for years.
And Amodei thinks that capability is enough to generate trillions of dollars in economic value.
He does.
Which brings us to coding. Because if you have a country of geniuses, surely they can write software. And if they can write software, shouldn't they be building the next better version of themselves? I mean, that's the classic singularity loop right there.
Coding is absolutely the first domino. Amodei is very clear on this. But we need to be careful with our definitions here because people hear AI coding and they immediately think it's going to replace all the software engineers tomorrow.
Right. And he lays out this spectrum of SWE, software engineering. He says it's not binary. It's not human versus AI. It's a progression.
Exactly. It progresses through these distinct phases. Phase 1 is 90% of lines of code are written by AI.
We're pretty much there, aren't we? I mean,
Yeah.
I use Copilot, I use Claude. They write the bulk of the boilerplate code for me.
In a lot of cases, yes, but that's actually a pretty weak metric. Just because it wrote the lines doesn't mean the code works or that it's architected well. So phase 2 is 100% of lines of code are written by AI.
So you're just a reviewer at that point.
Right. Then it gets more interesting. Phase 3 is 90% of tasks are done by AI.
Tasks. Okay, that's the key distinction. Because coding is typing. Software engineering is, well, it's suffering, mostly. It's compiling, setting up the environment, realizing the library version is wrong, writing the memo to explain why you did what you did, fixing the merge conflict.
All that glorious grunt work that isn't actually typing code but is absolutely necessary for coding to happen. And then finally, phase 4 is 100% of tasks are done by AI. At that point, you just give it a business goal.
And Amodei says his own engineers at Anthropic are already moving rapidly through this spectrum. They're using Claude to write GPU kernels, which is really hard, low-level optimization stuff that they used to have to write by hand.
Which implies a massive productivity boost inside these labs. But this raises a paradox, doesn't it? If the tech is already so good, why isn't the economy booming right now? Why isn't global GDP up 10% this year? If coding is 50% faster, software production should be going through the roof.
This is the diffusion lag.
Yes. The gap between what is technically capable and what is economically integrated. Amodei is very pragmatic and clear-eyed here. He gives the example of Claude Code.
That's their command line interface tool, right? The CLI.
Yes. An individual developer can download it and start using it in literally 5 minutes. Boom, their productivity goes up. But a large enterprise, a bank, a pharmaceutical company, a government agency.
Oh, forget about it. You need a legal review. You need a security compliance check. You need the CTO to sign off. You need a 6-month change management process. You need to retrain the entire staff. You need to make absolutely sure the AI doesn't accidentally hallucinate a command that deletes the main production database.
Exactly. Even if the AI can do the job perfectly today, it might take a big corporation 2 full years to figure out how to let it do the job. He calls it the corporate immune system. It attacks new things to keep the organism stable, even if the new thing is better.
So the prediction is, AGI, the country of geniuses, arrives in 2026. But the economic singularity, the point where GDP goes vertical, might trail that by 2 to 5 years.
Because of human friction. It's not a technical bottleneck anymore, it's a social and organizational one. He compares it to drug discovery. Even if an AI invents the cure for cancer tomorrow, I mean, literally just outputs the molecule structure, you still have to synthesize it, you still have to run FDA trials, you have to manufacture it, distribute it.
The compute part is fast. The physical world part is slow.
That's the whole story.
But he does push back on the idea that this diffusion will take forever, right? He says it won't be slow. His quote was something like, it will be fast, but not infinitely fast.
Right. He doesn't think it's going to be instantaneous Dyson spheres appearing overnight, but he also doesn't think it'll be like the 50 years it took for electricity to fully take over factories in the Industrial Revolution. It'll be somewhere in that messy middle.
Because the pressure to adopt will be too high to ignore.
The competitive pressure will be immense. If your competitor uses it and you don't, you simply die.
Okay, speaking of pressure, let's talk about money. Let's talk about the economics of the labs themselves. Because looking at Anthropic's revenue curve, it's bonkers.
It is a pure exponential. We're talking 10x growth every single year. From $100 million to a projected $1 billion to a projected $10 billion. It's just a vertical line.
Now, if I had a company growing 10x a year, I would be popping champagne. I would be buying a yacht. But Amodei, when he talks about this, he sounds stressed. He's talking about the risk of bankruptcy.
This is the CapEx bet, and it's a terrifying, high-stakes game of poker.
Okay, explain the hand they are playing. What's the bet?
Okay, so you know the model gets better with scale. You're Anthropic, and you want to build the biggest, most powerful data center possible for the year 2027. Let's say that costs $100 billion, maybe even $1 trillion over a few years.
Right.
You have to order the GPUs from NVIDIA today. You have to sign the power contracts with the utility companies today. You have to build the physical data centers today.
They made all that cash right now.
But the revenue you need to pay for all of that relies on the country of geniuses arriving on schedule. You are betting that the model you haven't even built yet will be smart enough to earn back that $1 trillion.
Ah, I see the problem. This is the gambler's ruin.
Precisely. If you predict the arrival of that next-level capability wrong by just 1 year, say it arrives in 2028 instead of 2027, you are dead. You have $1 trillion in debt, the data center is running up massive electricity bills, but the product isn't quite smart enough yet to generate the massive revenue you need. You go bankrupt.
So they are surfing this massive exponential wave, and if they lean too far forward and spend too much, they wipe out. But if they lean too far back and don't spend enough, they become irrelevant because a competitor like OpenAI or Google beats them to the genius country.
It is an unbelievably fine line to walk. And this dynamic, he says, forces the labs to be responsible, not just for abstract safety reasons, but for their own corporate survival.
And he says this explains why they are profitable or unprofitable in any given year, which I found fascinating.
Yeah, he mentioned this concept of a Cournot equilibrium. That sounded like an Econ 101 flashback for me.
Me too.
Yeah.
What is that in this specific context?
It's an economic model for an industry with just a small number of firms, like the AI labs. And he breaks down their internal economics like this. You spend roughly 50% of your available compute on training, that's R&D, building the next model, and you spend the other 50% on inference, that's serving customers and actually making money.
Okay, that seems like a pretty balanced split.
It does. But here's the totally counterintuitive kicker. Profit, oddly enough, usually happens when a lab underestimates customer demand.
Wait, really? That seems backward. Usually you profit when you sell a lot of stuff.
Think about it. If you underestimated demand, it means you didn't buy enough chips to serve both your R&D efforts and all your new customers. So you have to steal compute from your R&D budget to serve the paying customers.
So your research for the next model slows down.
Your R&D slows down, but your revenue looks fantastic relative to your costs, so you make a profit.
And conversely, if you overestimate demand,
you bought too many chips, you have idle compute just sitting there. So what do? You dump all of it into R&D. You make amazing progress on the next model, but your balance sheet looks terrible because you have these super high costs and lower than expected revenue.
so profitability in an AI lab right now is actually a sign of bad planning, or at least overly conservative planning.
In this specific hypergrowth phase, yes. It suggests you aren't reinvesting aggressively enough in building that next exponential step. If you're making a big profit, the logic is you should have bought more GPUs.
That is a wild way to look at a P&L statement. Oh no, we made a profit this quarter, we're failing.
It's the logic of the singularity. Normal business rules just don't apply when your growth rate is 10x per year. You are either growing at an insane pace or you are dying. There's no in between.
Okay, let's pivot. This is a big pivot. We've talked about the tech, the timeline, and the money. Now we have to talk about the safety. Because if we are actually building a country of geniuses, we probably want to make sure they don't, overthrow the government or help a terrorist build a bioweapon.
This brings us to constitutional AI. This is Anthropic's flagship safety and alignment approach.
And it's time for a neural signal check. What is the core technical shift here? Because for a lot of people, AI safety just sounds like censorship. It means, I'm sorry, as a large language model, I can't tell you a joke about a banana.
Right. And the fundamental shift is from thinking in terms of rules to thinking in terms of principles.
Unpack that for me. What's the difference?
Okay, so the old method of alignment, which was mostly RLHF, reinforcement learning from human feedback, was based on a huge list of specific do's and don'ts. Don't be racist, don't speak in Korean, don't tell people how to hotwire a car.
I think checklists of bad things.
Exactly. But checklists are brittle. They're easy to break. You can't possibly list every single bad thing in the universe. If you have a rule that says, don't tell people how to hotwire a Ford, the model might turn around and tell you exactly how to hotwire a Chevy because it wasn't technically on the list.
Or it might just tell you how to short-circuit the ignition system, carefully avoiding the word hotwire.
Exactly. It's a constant game of whack-a-mole. Constitutional AI is fundamentally different. Instead of rules, you give the model broad principles to follow. Be helpful. Be harmless. Respect the user's autonomy. Be as objective as possible.
It sounds a little vague,
Yeah.
like one of those corporate values posters you see on lunchroom wall.
To a human, maybe it does sound vague. But technically, Amodei says that models trained on these broad principles generalize much better. They are more robust across an infinite number of edge cases. If the guiding principle is don't help with violence, the model can infer that hot wiring a car could be related to violence or theft without needing a specific rule about every make and model of car.
It derives the specific rule from the general principle.
Precisely.
So how do they update this constitution? Is it just Dario sitting in a room somewhere writing commandments on stone tablets?
He describes it as 3 feedback loops. First is the internal loop. Anthropic's own team tweaks it based on the training data they see. If they notice the model is getting too aggressive in debates, they might tweak the politeness principle.
Makes sense.
Second is a competitive loop. This one is really interesting. He calls it the marketplace of personalities.
The marketplace of personalities. I like that.
Right. So OpenAI has a constitution, Anthropic has one, Google has one. Maybe OpenAI's model is a bit more move fast and break things, and maybe Anthropic's is a bit more cautious and thoughtful. The market ultimately decides which personality is more useful for which tasks.
So if you want a yes man to just do what you say, you buy Model A. If you want a more responsible, thoughtful advisor, you buy Model B.
That's the idea. And the third loop is societal, getting input from democratic processes, from governments, from the public. But he admits that one is very, very slow. Democracy doesn't exactly run on a 2-week agile sprint cycle.
Speaking of democratic processes, the conversation took a pretty sharp turn into geopolitics. And Amodei has a very specific worldview here that informs their strategy, what he calls the offense-dominant world.
This is a crucial concept to understand their thinking. In military strategy, a defense-dominant world means it's easier to defend your territory than to attack. Think of a medieval castle. You need a huge army to take a small castle.
Right.
An offense-dominant world means it's easier to attack. Think of nuclear weapons. You can't really defend against them. You can only deter by threatening to retaliate.
And he's arguing that AI pushes us much further towards an offense-dominant world.
That's the big fear, specifically in areas like cyber warfare or bioweapons. And AI might make it trivially easy to find a zero-day exploit in a power grid or to design a brand new, dangerous pathogen. And defending against that, patching every single hole, monitoring every single biology lab in the world is much, much harder than creating the attack in the first place.
And this is the strategic justification for the export controls on chips.
Yes. This is why the U.S. government is denying high-end chips to China. It is a resource denial strategy. If you believe the world is offense dominant, then you believe you absolutely must maintain a compute lead over your adversaries. You need your defensive AI to be smarter than their offensive AI so you can catch the attacks before they happen.
You need your AI to scan the code and find the bugs before their AI finds the exploits.
That's the game theory of it, yes.
But I found myself asking, and the host Gorkish asked this too, do you really need the best, most cutting-edge AI to be a villain?
And that's the North Korea counterpoint. It's a great question. Amodei's fear isn't just about a peer competitor like China having a slightly better model. It's that you don't need state-of-the-art AI to effectively oppress a population. You just need good enough AI.
A mediocre AI can still run a surveillance state perfectly well.
It can read every email, it can listen to every phone call, it can analyze every video feed, and it can flag dissent with brutal efficiency. It doesn't need to be able to write poetry to do that.
Which is a genuinely chilling thought. So we had this global race. Can the democracies build the country of geniuses fast enough to set the rules of the road for the entire post-AI world order?
That is the geopolitical wager being made right now. Amodei seems to believe that if the democratic labs get there first, they can structure the global governance of this technology to protect liberal values. If the authoritarian states get there first, well, the global equilibrium looks very, very different.
Heavy stuff. But let's zoom back out for a moment. We've covered a lot of ground here. Scaling, timelines, the economics, the geopolitics. It's a very comprehensive picture he paints.
It really is. He's thought through a lot of the second and third order effects.
So to recap the whole deep dive, the exponential is ending, but only because it's about to go vertical. The big blob of compute is eating everything, including reinforcement learning. Coding is the first major domino to fall. and 2026 or 2027 is the target date for a capability explosion that could look like a country of geniuses.
That's a summary in a nutshell.
Now, before we go, I have to mention one last detail from the interview that I just absolutely loved: the Dario Vision Quest.
The DVQ. I laughed when I read this part. It's great.
Yes. Apparently, Dario Amodei communicates with his entire 2,500-person company via these things he calls Dario Vision Quests. There are these long 4-page memos and then unfiltered Q&A sessions.
It sounds kind of funny, but when you think about it, it's actually a vital part of the internal alignment strategy. It's about creating high bandwidth trust.
Right.
In a world that is moving this fast, you can't rely on generic corporate speak and PowerPoints. You need every single person in the boat rowing in the exact same direction, understanding the exact same nuance. If the CEO thinks we are 2 years from AGI and the junior engineers think we are 10 years away, the company just tears itself apart.
It's a really great leadership insight, actually. Okay, Neural Intel listeners, that brings us to your final provocation for the week.
We've talked a lot today about the lag between technology and adoption. So here's the question for you to chew on. If the country of geniuses is truly only 2 years away, and corporate diffusion of new tech takes, say, 5 years, are you building your infrastructure for the AI that exists today or for the AI that will exist when your project finally launches?
Because if you're spending 2 years building a system based on GPT-4's capabilities, you might be completely obsolete before you even deploy.
Precisely. You have to skate to where the puck is going to be, not where it is right now.
We really want to hear your take on this. Is the exponential actually ending, or is it just getting started? Are you buying the big blob hypothesis? Let us know in the comments.
And don't forget to check out the full technical breakdown over at neuralintel.org.
Thanks for listening. We'll see you in the deep end next time.
Goodbye.